In this video, I'm going to tell you 1. What dark matter is, 2. The 2 rules you need to know in order to really get why we believe in dark matter, and 3rd, 3 pieces of evidence for the existence of dark matter. So let's jump right into it. First, what is dark matter? I'm going to give it away right away. Dark matter is probably a weakly interacting massive particle. By weakly interacting, we mean that it's interacting with gravity, and it might be interacting with a heretofore unknown force that's stronger than gravity, but weaker than the weak nuclear force. This particle, we don't exactly know its size, but it's thought to be pretty big, hence massive particle. These particles are called WIMPs, which is just an acronym for weakly interacting massive particle. Before we jump into the evidence for dark matter, let's get a sense of the 2 rules you need to know in order to understand why these experiments and why these discoveries actually lead us to believe in dark matter. The first thing you need to know is something very basic, which is if you have something orbiting another thing, the velocity of the object in orbit has to be a very specific velocity to stay in orbit. Because if it's going too fast, it's going to just fly out of orbit, and if it's going too slow, it's going to come into the orbit and crash into that center of mass. So for example, if we're dealing with the sun being orbited by the Earth, if the Earth were a little faster, it would fly out of its orbit, and if it were a little slower, it would come tumbling into the sun. That's the first step. The second rule to know is the question of what causes gravity. And given our current understanding, gravity is caused by the curvature of space-time, which for our purposes, we can just think of it as the curvature of space. And that is caused by matter. Einstein's famous equation, E equals mc squared, energy equals matter. So energy or matter, mass energy, causes gravity, causes curvature of space. Okay, now we have the 2 steps that we need to understand the discovery of dark matter. To that end, let's jump to the first piece of evidence. The first piece of evidence comes from looking very closely at the speeds at which stars on the edge of our galaxy are orbiting our galaxy. By looking at the stars right beyond the edge of our galaxy, now obviously there are stars there, so it's not beyond the edge of our galaxy, but it's beyond what we would think of as the edge of our galaxy. It's beyond the spiral arms. It's these stars that are just distributed a little beyond those spiral arms, and there are very few stars there. We expect the velocity of those stars to be orbiting the galaxy increasingly slowly, but that's not what happens. Instead, it orbits at roughly the same speed as those stars that are a little closer in, and the same thing the farther out we go, the orbits are roughly the same. This is a problem because what we're seeing is that it's going at an orbit that, based on our understanding, it should fly out, but it's not flying out. It's staying in a stable orbit. The only explanation that we have for that is our understanding of gravity. And our understanding of gravity is dependent on mass. So in other words, at that speed, it's acting as if there's more mass inside, within the orbit, towards the center, than we can see. We see a gravitational effect in the orbit, and we can infer from that gravitational effect that there must be mass energy sitting somewhere here, because that's what causes gravity. A similar logic explains the other 2 pieces of evidence that I'm going to go through in this video. The second is, instead of stars orbiting a galaxy, think about galaxies orbiting a galaxy cluster. Again, the farther out we go beyond the main area of concentration, where the farther out you go, you're actually dealing with less and less matter progressively, well, you expect those galaxies to slow down. And lo and behold, that's not what we're seeing. And lastly, the third piece is again using gravity, but this time in a slightly more sophisticated way, in a way that relies on relativistic effects, namely the curvature of light by gravity. This last effect can be seen whenever there's a big mass. So in this image, we're looking at a galaxy cluster, and behind this cluster are a number of sources of light. But that light's getting curved and distorted as it passes by or passes around this galaxy cluster. And you can see with those pink slivers in a slightly circular shape around this galaxy cluster, those slivers are those distortions. And we can measure those distortions, and we can measure the speeds of these galaxies that are orbiting other galaxies in a galaxy cluster, and we can measure the speed of these stars orbiting around our galaxy and other galaxies. And we can calculate from that how much mass are we dealing with. And the answer is, it depends a little, depending on what scale we're measuring at, because dark matter doesn't distribute itself perfectly evenly. But the net story is that we have just about 6 times the amount of dark matter as ordinary matter, and that equates to about 4% of matter being ordinary matter, 23% being dark matter, and the remaining 73% waiting for our next video on dark energy. Before ending this video, however, I want to give you a sense of what this distribution actually is. Here's an artist's depiction of the Milky Way galaxy. And this depiction shows in blue the dark matter distribution. And you could see that from our measurements, we've gathered that dark matter is distributed roughly spherically around the galaxy, and it gets more and more concentrated towards the center of the galaxy. In fact, when we get to the center of a galaxy, very often we're dealing with something like a 1-to-1 ratio of dark matter particles to regular matter particles. So that's dark matter. In the next video, we're going to tackle dark energy. If you'd like to know everything, subscribe.